Hi everyone. Today we're going to be comparing linear, quadratic, and exponential models. We've actually touched on this a little bit earlier in a different video, but we're going to be talking about it in depth today. So our objectives for today are to compare the three models against each other, and then to determine which type of function best models a given set of data, be that in a table or a graph, and then use that to write an equation for the function. So there are three aspects of functions we can look at to determine whether a function is quadratic, linear, or exponential. And these three aspects are tables, graphs, and equations. These three will tell us all the information we need to make a decision about which model we have. Let's take a look at tables first. So if we have a table with a bunch of values, something like this, for constant differences in x terms, so that means like if the x's all move up by the same amount each time, linear models will have a constant first difference between the y terms. So this is first difference. And what I mean by that is that if we look at the y terms, they all move up by adding the same number or subtracting the same number. Quadratic models have constant second differences. And I know we've seen this before, but it might have been a little while. So second differences are the differences between the differences. So that's like, here we have 3 and plus 3 and plus 3. Our second differences would be the differences between those. Quadratic models will have constant second differences. Exponential models will have constant ratios between terms. Ratios are where we multiply one term by something to get the next term. We always want to multiply by the same number. All right, let's look at graphs. So for graphs, there are a few different ways we can tell which function we have. So if we have a linear function, our graph is going to be a line. It can be straight up and down, side to side, or something like this. If we're having a quadratic function, it's always going to be a parabola. So it's either going to be upward facing, like the one shown here, or it can be downward facing, like a frowny face also. If we're looking at exponential functions, our graph is going to slope upwards or slope downwards. The main difference between these two is that quadratics end up going up and then up on the other side, or down on one side and then down on the other side, whereas exponential will only go up in one direction. All right, now let's look at equations. If we're looking at equations, there are also a few different ways we can tell these apart. So a linear function will always have only an x term. It will not be x squared, and x will not be in the exponent. So we have three different types of equations here. We have our standard form, our slope-intercept form, and our point-slope form. But no matter what form we have, x is always just x. Never squared, never in the exponent. For quadratic, however, our x will always be squared. We'll have y equals and then some numbers, but always an x squared in there. For exponential functions, we always have x in the exponent. So, and like it says in the name, exponential has exponent in it. So you can always remember that x is going to be in the exponent. So here we have y equals ab to the x. That's exponential. All right, let's do some problems now and try to differentiate between some functions that were given. Okay, so for the next three problems, we're going to want to determine if a model is linear, quadratic, or exponential. How are we going to do this? We're going to examine a table, a graph, and an equation. So let's look at a table first. We have this table given to us, and our x's move up by a constant amount. So we can examine our y's and see if we have a constant difference, a constant second difference, or a constant ratio. So let's see. It's always good to examine differences first if you can, because ratios might get a little more difficult. So let's see about our differences here. We go from 40 to 33. That's a difference of -7. From 33 to 28, that's a difference of -5. And from 28 to 25, that's a difference of -3. Clearly, our first differences are not the same, but let's look at our second differences. From -7 to -5, we're adding 2. From -5 to -3, we're also adding 2. Because our second differences are the same here, that means we have a quadratic function. So this guy is quadratic. All right, let's look at a graph. In this graph, we're given a line. So clearly this graph is linear. This is probably the easiest way to tell a function apart from one another. This graph is linear. Remember, if we had a parabola, we'd be quadratic, and if we had a sloping upwards or sloping downwards, we'd be exponential. All right, now let's look at an equation. So the last way we can tell our functions apart is by using an equation. So in this equation, we have y equals 3 times 5 to the x. The thing that gives away the type of function here is the fact that x is in the exponent. That means we have an exponential function. So this is exponential. If x were on its own and not in the exponent, we'd have a linear function. And if x were squared, we'd have a quadratic function. So now that we've learned how to identify functions, we can explore our options further. We can do more than just identify functions. We can find a model's equation. So this guy right here is equation. And we can do this for linear and exponential models. We are able to do this for quadratic also, but we're only going to be focusing on linear and exponential. So what's our objective here? Well, we want to write an equation to describe a function. How are we going to do this? By examining the information we're given in a table or a graph. So first, in the fourth problem, we're given a graph. And our graph looks like a line, so we know it's going to be linear. So we have a few different choices for our equation. We can either have slope-intercept form, point-slope form, or standard form. My favorite is slope-intercept form because all we need to find is the slope and the y-intercept. And we have both of those things at our fingertips here. So we can examine this. What's our y-intercept? Our y-intercept is going to be this point right here. That's 1. So our y-intercept is 1. Our slope, we are going to have to pick 2 points here and figure it out. So rides over run. If we go up 1 here, we go backwards 1. So that's 1 over negative 1. 1 over negative 1, which equals negative 1. So now we can use our equation for the slope-intercept form, which is y equals mx plus b, and we can fill in what we know. So y equals the slope times x, so that's negative 1 times x, plus our y-intercept, which is 1, plus 1. We can rewrite this if we want to. This is fine, but we can simplify it to y equals negative x plus 1. And we're done. Okay, in this problem we have a table. So we're going to have to do a little bit of work to figure out which function we have in the first place. We're going to want to look at differences, second differences, or ratios to figure that out. So if we were to look at the differences between these terms, we would see that we neither have the same first differences nor the same second differences. So that means that we probably have a common ratio. And as it turns out, we do, and it's 3. 1 times 3 is 3, 3 times 3 is 9, and 9 times 3 is 27. So that's our common ratio, and we know that it's exponential. Exponential functions have common ratios. So now that we know it's exponential, we can use what we know about exponential functions, which is their equation. That's going to be y equals a times b to the x. Now we have to figure out what a and b are. So a is going to be the y term when x is 0. So whenever x is 0, we can look at the y term right here, which is 9. So that means a is going to be 9. B is going to be our common ratio, and that's 3. Now we can just plug in what we know, and we'll have an equation. So that's going to be y equals 9 times 3 to the x. Just like that. And we have our equation. All right, I will leave you to try the problems at the bottom of your guided notes. Thanks.